All right, so chapter 5 is all about chemical accounting, basically keeping track of atoms, molecules, moles, and things like that. So we have a lot of practicing to do. And the first thing we're going to do is actually something we went over a little bit in lab. And we're just going to discuss chemical equations and how to bounce them. And with a chemical equation, it's a representation of a chemical reaction. So for example, you can have some reagent that typically goes on the left-hand side. So this is a made-up reagent, AB. And in this reaction, we're going to show it proceeding with a one-way arrow going to two new reagents, A plus B. And so typically when we show this, you have molecules on the left, molecules on the right, but you need to pay really close attention to how many molecules and atoms are on each side. And that's referred to as bouncing. Oops. And it takes a little bit of practice to get good at, so we're going to actually spend most of today just working through practice problems. And let's quickly define why we're doing this. There must be the same number of elements for the starting material side as the product side. And I'm just going to abbreviate product PDT. And really this all relates to conservation of mass, right? You can't really create or destroy atoms short of doing some sort of nuclear reaction. Okay, so let's practice one. And in this reaction, we're treating magnesium, Mg, with hydrochloric acid, which is HCl. And when you mix magnesium metal with hydrochloric acid, you generate hydrogen gas, which is H2. And you generate this compound. What would this be called? Just as a review. Not everybody all at once. I can't hear you when you all talk over one another. Magnesium chloride, right? A lot of students are tempted to say magnesium dichloride. We don't include mono, di, tri, tetra with ionic compounds. And we know this is ionic because it has a metal in there, right? Okay, so in bouncing a reaction, we have to include reaction coefficients. And what they are is basically a multiplier. And so a multiplier can come before any one of these. And what I like to do is just count atoms, right? So for example, over here, I've got one magnesium, so 1 times Mg. Over on the right-hand side, I also have one magnesium atom. So that looks good. Magnesiums bounce. Let's move to hydrogen. On the left-hand side of the arrow, looks like we have one hydrogen. And on the right-hand side, we have 2 hydrogens. That means we need to fix this, right? The hydrogens aren't bounced right now. So a simple solution would be, let's just multiply the entire HCl unit by 2 with a reaction coefficient. So now if I do that, I've got 2 hydrogens on the left, 2 hydrogens on the right. Make sense so far? We haven't changed the magnesium, otherwise we would need to go back and change that as well and ensure that the magnesium is balanced. So now we need to double check our last element, which is chlorine. Now we have 2 chlorines on the left, and we've got 2 chlorines on the right. So like I said, you want to use these coefficients as multipliers. And some students get confused by this too, right? When you look at the reaction coefficient, you're not just saying 2 hydrogens, you're saying 2 HCl. So really, what you're looking at is multiplying the entire HCl by 2. So 2 hydrogens and 2 chlorines coming out of it. Does that make sense? People do get confused too between regular size numbers and the mini numbers that go down below. It's important to remember that if you see a 2 here, that means you have 2 chlorines, but if you see a large 2 in front, that means 2 of the overall molecules. So you do have to pay attention to subscripts versus normal size numbers. So I'll show you some hints for bouncing chemical equations because some of them get really challenging. And the first hint involves bouncing one element at a time. Sometimes when you look at really complicated reactions, it's easy to get overwhelmed. When you get overwhelmed, your brain locks up and you can't do anything, right? So just focus on one individual element, bounce that, move to the next element, bounce that, and so on. The second one is leave individual elements alone until last. And I'll show you what I mean by that. So for example, if you have sodium by itself, you want to leave that alone until last. If you have hydrogen gas, which is just elemental hydrogen, only containing hydrogen, leave that till last. You see O2, leave that till last. Anything that is only made up of one atom or one type of atom, leave that alone until very last. Those are easy to fix. And then the third one is if you get stuck, double your most complex compound and start over. All right, so let's do a few practice ones, and then I'll let you guys work on the practice activity in small groups. So I'll do one of my favorite ones. We have hydrogen gas, which is H2, and oxygen gas. And we react this together. What do you think we're likely going to make? H2O, right? So water. Okay. We have to determine whether or not this is balanced, and if it's not balanced, we need to add in those reaction coefficients. So, for example, if I start out on the left-hand side, I've got 2 hydrogens. Right-hand side, 2 hydrogens, so hydrogens look good. If I look at oxygen, I've got 2 on the left, but only 1 on the right. So I'll go ahead and double this. Am I done? No, now I have 4 hydrogens on the right-hand side, but only 2 on the left. So we can go ahead and plug this in. Sometimes it's nice to have a visual representation too. So for example, we've got 2 hydrogen gas molecules reacting with 1 oxygen molecule, and if you remember, the Lewis structure for oxygen contains a double bond. So it looks like that. And when you react these together, you end up with 2 equivalents of your water coming out. So if we look on the left, we've got 4 hydrogens, on the right 4 hydrogens, on the left 2 oxygens, on the right 2 oxygens. So it's a good visual representation of what's occurring. I like this reaction. I think I mentioned this before, that this is actually what they used to fuel the space shuttle. So that big orange tank was full of liquid hydrogen and liquid oxygen. And when they combust, they form water. So really the exhaust you see coming out the end of the space shuttle is primarily water vapor. It's a very clean reaction. A lot of people don't appreciate how violent this reaction is, though. So I wanted to show this. Oops.
All right, so let's dispel a common belief.
Oh, no. It's not loud. Just 1 second.
Oxygen is not combustible. Oxygen just helps other things that are on
I'll
fire.
restart it.
It just makes the fire spread
My fingers are too fat to adjust this.
a lot further.
There we go.
So here's a balloon, for example, that has nothing but pure oxygen inside, and I'm going to light on fire. All right, here we go. Pure oxygen. Stand by. Here we go. Watch. See? Nothing at all. Now, if there was something that could catch on fire there, then that would be a whole lot better. So that's where we have this. A bouquet of just balloons for like an ordinary birthday. Except these balloons happen to be filled with hydrogen, and a couple of them happen to have a mixture of hydrogen and oxygen. So I want you to kind of see what this looks like when this goes. And Trustee Jeff here, my assistant, is perfectly safe. You can see No concerns at all. These are my thought protectors, so we are ready to go. Okay? All right, here we go. Ready? Here we go. Wow.
So I used to do that demo until I was asked not to. One time we did it, and if you look up at this bounced equation, right, the whole goal with making your balloon is to have a perfect 2-to-1 ratio of hydrogen to oxygen. And we did a few trial runs, and we were pretty close to 2-to-1, and it was loud. And then we did the demo in a classroom where we nailed 2-to-1. You could see a shockwave ripple across the room. We almost blew out windows, and people ran up from 3 stories below us because they thought something really bad happened. So we were asked never to do that again. I really like showing that video just because it reminds me of getting yelled at. All right. So, let's do some practice ones. All right, so for the first one, I've got sodium and water. This is another violent reaction. And this reaction is violent because you produced sodium hydroxide and an explosive gas, hydrogen. There's actually a cool video you can look up on Wikipedia where after World War II, I think it was the Navy or Army decided to dispose of a bunch of sodium by dumping it in a lake. Probably not the best idea. So that's the first one. Then we'll do this one. What's this molecule called? SiCl4. It's covalent, right? It's between nonmetals, so we do need the mono, di, tri, tetra. So it'd be silicon tetrachloride, right? So you don't say monosilicon, you just leave it alone because it comes first. So silicon tetrachloride plus water is going to combine to form another unique molecule, along with hydrochloric acid. So that will be our second one. And then our third one I want you to practice with is with phosphoric acid, one of the stronger acids out there. It's going to decompose. Whoops, this should be H4. P2O7 plus water. So I'll give you some time to work on this and then check with your neighbor and see if you agree. If you think you got them all, give me a thumb so I know. If you're done too, I'll give you a challenge one. They get harder in biology. C2H2 plus O2. Has anybody done welding? Welding, so this is the reaction for welding, right? So when you get a welding tank, you have acetylene, which is C2H2, and oxygen, which is O2. So oxyacetylene is this reaction. When you do that combustion reaction, you create CO2 gas and water. So let's see if you can bounce that one if you've got the first three done. All right, so let's try this as a group. We'll just work through this slowly. Like I said, I like to leave individual elements to last, so I'm going to skip sodium just because it's easy to bounce that one out, and I'm going to focus on water next. So let's think about the oxygen, for example. Oxygen, I like starting with oxygen because it's the heavier atom in the molecule, so if you can, try to start with the heavier atom. If we look on the oxygen on the left, we've got one. Oxygen on the right, we've got one. So we're kind of stuck there. Now we look at the hydrogen on the left. We've got two, and on the right, we've got three. One tricky thing is you can't have an even number on one side and an odd number on the other side, right? So one good trick I'll show you is right here. We've got an odd number of hydrogens. How can we get this to an even number? What happens if I multiply this by some number? Even number times any number is still going to be even, right? But what about the sodium hydroxide? Maybe I'll do a number there. Now it looks like I've got 4 hydrogens on the left, 4 hydrogens on the right. Do you see that? So now it looks like we've got even numbers on the right, even numbers on the left. However, we're not fully balanced. What should I do to get 4 hydrogens on the left-hand side? Yeah, put a 2 in front of the water. Okay, so now let's go through and check. Really, really slowly. We'll just start with oxygen. We've got 2 oxygens on the right, 2 oxygens on the left. Looks like it's checking out. Then we'll do hydrogens. Got 4 hydrogens on the left. How many do we have on the right? Looks like just 4, right? We've got 2 hydrogens in this set and then 2 over here. So it looks like we've got 4 total hydrogens over there. So it looks like the hydrogens and oxygens are balanced. Now we need to look at the sodium. Sodium is an individual element, easy to balance. However, we only have 1 on the left and 1 on the right. So what should we do? Put a 2 in front of the sodium. So now if we go through and check, it looks like all of the elements going in are coming out the other side, right? All right, let's do the second one. Second one, if we look at the silicon, I've got 1 silicon on the left, 1 on the right. That looks good to me. We've got 4 chlorines on the left, but only 1 on the right. So I'm going to multiply this by 4. So now we've got 4 chlorines on the left, 4 on the right. We haven't changed the silicons. Okay, so that looks good. Now we've got to deal with the water, right? If we look at the oxygen and water being the heaviest atom in there, we've got 1 here, but we've got 4 over here. So an easy solution to that would be multiply water by 4. Okay, so now when we do that, whoops, we've got 4 oxygens, 4 oxygens. Now we need to think about our hydrogens. How many hydrogens do we have in water now? 8. So 4 times 2 means we have 8 total hydrogens in those water molecules. And when we go over here, we've got 4 hydrogens in this compound and 4 over here. 4 plus 4 is 8. It looks like it's completely balanced. So some of these look much scarier than they are. The trick is not getting flustered. If you get flustered, like I said, that's when things go sideways and you become your own worst enemy. Your brain freezes up. All right, last one of the regular set. If we look at, let's say, the heaviest atom here, the heaviest atom in phosphoric acid is phosphorus. So I'm going to start there and say, all right, over here we have 1 phosphorus. Over here we have 2 phosphorus. Okay, that means we need to balance the phosphorus. So I'm just going to go ahead and multiply this by 2. That means I've got 2 phosphorus atoms on the left and 2 on the right. So that looks good to me. All right, next heaviest atom looks like oxygen. So now we've got 2 times 4 is 8 total oxygens over here. Then over here we've got 7 plus 1 equals 8 oxygens on the right-hand side. So it looks like it's balanced there. And then we could look at the hydrogens, right? On the left-hand side, we've got 6. How many do we have on the right-hand side? 6 too. So you can go through and kind of make a list of atoms in, atoms out. These problems are really good to do on scratch paper too. So if you need to, use all the scratch paper you need and just adjust it as you go along. It does get kind of confusing. All right, let's try the challenge problem together. So the challenge problem, let's start with carbons. That's the heaviest atom in our first molecule. Over here we've got 2. Over here we have 1. So really quickly we can say, well, we need to multiply the CO2 by 2. All right, now we've got 2 carbons over here on the left, 2 carbons over on the right. Looks good to me. All right, now we'll go to the hydrogens over here. Looks like we've got 2 hydrogens here, 2 hydrogens here. Looks good to me. All right, and then over here, last but not least, we've got oxygen. I'll just change colors. We've got 2 oxygens here, and then we've got 4 oxygens in CO2 because we've got 2 of them, plus 1 over here equals 5. Looks to me like we're a little stuck, right? So what was the hint I gave you if you ever get stuck?
Double your most complex.
Yeah, double your most complex molecule, which in this case is going to be this one on the left. So now I'm going to restart. Just erase this and kind of start over again. Again, we'll start with carbons. Now we've got 4 carbons on the left. Over here we only have 2, but we can fix that. Let's change this to a 4. Now we've got 4 carbons on the right-hand side. Look good? Then we'll go to hydrogens. I'll do hydrogens in blue. We've got 2 times 2 equals 4 hydrogens over here. And then over here, it looks like we only have 2, but we can fix that by multiplying it by 2 to get 4 as well. So I'll go ahead and plug in a coefficient 2 over here. Oops. So now our hydrogens are balanced, our carbons are balanced. Last but not least, let's do oxygens. Over here, we've got 2. Over here, we have 4 times 2 would be 8, plus 2 oxygens from water is 10. So over on the left-hand side, or sorry, right-hand side, we've got 10. On the left-hand side, we have 2. So how can we fix that? Put a 5 in front of the O2. So now when we go ahead, we can say 2 times 5 equals 10. It looks like all of our atoms are bouncing out on the left and right. Does that make sense? Don't be afraid of starting and stopping over. If you are stuck, doubling it sometimes gets you out of that jam. Or you can use that even odd trick that I was showing you earlier. Some people feel really comfortable doing that. All right, because I know this is really complicated, I'm going to give you guys a jump start on the problem of the day. My goal is that everybody can knock out those first 10, and then the additional problems are just to keep you working on this so that you feel really confident bouncing equations. The remaining part of the chapter, we can't really do well unless we know how to bounce equations.